Hey guys, so in the email that I sent out to you guys last week, I got a question that was a very, I guess a really maths question instead of a strategy question, but that's cool because it's something that I probably should cover at some point. And it was dealing with finding solutions for equations. So you've say got a quadratic and maybe a linear equation, and a question specifically asking for a number of solutions. So it might be a unique solution, might be no solution, might be infinite solution. So I've come up with a bit of an example just to walk you through the typical steps that you take with these problems. But a lot of the time what these questions come down to is not actually finding the solutions, it's just coming up with a way to describe how many solutions you might have. So have a look at this problem. I've got two functions, f of x, which is x squared plus k plus 1x plus 4, and then I've got g of x, which is 3kx minus 3. And the question asks us to find the values of k such that f of x equals g of x has a unique solution. So the first thing we want to do is probably actually let f of x equal g of x, which means we'd be left with x squared plus k plus 1 x plus 4, and we're going to let that equal 3k x minus 3. Now, normally, if we were trying to find the actual solution, so find the values of x, we would hopefully spot that this is a type of quadratic problem, move everything over to the one side so that it equals 0, and then go through the methods that we would usually use to solve quadratic equations. So we're going to start with that at the very least. We're going to go x squared plus, and I'm going to expand this out just so it's a little bit easier to follow, but you don't necessarily have to expand this out. Kx plus x plus 4, and then I'm going to minus 3kx plus 3 equals 0. And then what I'm going to do is just collect as many like terms as I can. So there's no like terms with the x squared, but there are 3 like terms that have an x. I've got a k, I've got one with just a 1, and I've also got the negative 3k. So kx minus 3kx is negative 2kx, and then you've just got the x by itself. So what we can do is just simplify that up a little. So I'm going to have plus, and I'm going to have negative 2k plus 1x. So what that is the collection of all the different terms that I was using with the x factor. So that would be this one right here, this one right here, and this one right here. I've combined all 3 of those terms. You would get negative 2kx plus x, and then I've pulled out x as a common factor. And the reason I do that is because I want a single coefficient for the x term, because that's going to be our b if we were to use, say, the quadratic formula. Then I've also got the plus 4 and the plus 3, so together I'm going to make that plus 7, let it equal 0. Now at this point you usually have a few options. You would say factorize it if you were looking for the solutions. You could also use the quadratic formula if you were looking for solutions. The issue here is that we're not actually looking for solutions. We are looking for the number of solutions, which is a completely different story. We are after how many solutions a problem has, not necessarily what those solutions are. We're interested in making sure that the problem has a unique solution and then finding the values of k that would make that happen. Now conveniently, there is a nice little trick for seeing how many solutions a quadratic has. Basically, it comes down to the discriminant, which is the bit inside the quadratic formula, inside the square root function. So if you've got the quadratic formula, which looks something like this, you've got negative b plus or minus the square root of b squared minus 4ac, the whole lot over 2a. By the way, if you haven't had a chance to memorize this formula, this is definitely one that you do want to memorize, but the discriminant specifically is this bit right here. Now this bit actually defines how many solutions a quadratic might have. If that section is equal to 0, the equation will have one solution. If that particular section is greater than 0, so it's a positive number, you'll have 2 solutions, and if it's less than 0, you'll actually have none. So that actually suits our situation rather perfectly because we're hoping for a unique solution, which means what we can do is we can basically take that discriminant, let it equal 0, and then figure out what k would be to make that happen. So that's what we do. We're going to take our b squared minus 4ac, and we want that to equal 0 because we want a unique solution. In this particular case, that's 1 minus 2k, which is the same as negative 2k plus 1. I'm just rewriting it a little bit neater. We're going to square that. We're also going to minus 4 times a times c, and we want that to equal 0. Now, be careful here. We don't want it to equal 0 because this equals 0. That's not what we're doing here. We want it to equal 0 because we want the discriminant to equal 0, because that would mean that we have a unique solution. So this 0 and this 0 are coincidence and nothing more. It's important that you have this 0 here because otherwise the quadratic formula doesn't work. And it's important you have this 0 here because otherwise it doesn't fulfill the requirements of the question that we're interested in. But they're not the same thing. That's really important. It is entirely possible to have this one equal to 0 and this one equal to something else if we were after, say, a different set of conditions. So, we've got our little equation that we can work through, and all we have to do here is solve what k would be in this particular case. So, all that's left here is a little bit of algebra. So I've got 1 minus 2k, whoops, squared is minus 28 is equal to 0, which means 1 minus 2k squared is equal to 28, which means 1 minus 2k is equal to the square root of 28, plus or minus. Negative 2k is equal to negative 1 plus or minus the square root of 28, which is probably better written as negative 2k equals negative 1 plus or minus 2 square root 7. It's always best to simplify your surds where you can. And then just divide by negative 2 to finish it off. So that's going to make this a positive 1. Plus or minus basically becomes minus or plus, so that we don't need to deal with that. Over 2. And those are the two k values that actually make this equation have a single solution. So what that actually means from a graphical point of view is if k were to equal 1 plus 2 root 7 over 2, then the line and the curve would have a single intersection point. The reason that we get two possible values is because of this. And I can sort of try and visualize, but it's a little bit hard with a fluid value of k. But if you can imagine that your quadratic is a positive quadratic, it's definitely got a y-intercept of 4, so I'm just going to work with that. And I'm going to say that it looks something like this. Now, obviously it will change slightly depending on what the value of k is, but overall it's probably going to be something like this. If you've also got a linear equation that's, got maybe a positive gradient, maybe a negative gradient, but the y-intercept is definitely negative 3, that would be somewhere like this. And there's two values of k that would mean that this line matches perfectly up with the parabola at a single point. So maybe something like this, or maybe something like this. So there are two distinct values where a line that has a y-intercept of negative 3 could intersect at a single point with the parabola. At any other value, it's either going to do one of two things. It's going to intersect twice, so boom, boom, or alternatively, it's going to not intersect at all, which would be what would happen if we did something like this, which would just never reach the parabola. But at those values exactly, if k were to equal either of those values in both the quadratic and the linear equation, then the line and the parabola would have exactly one intersection point. So just to recap, what we did is we let the equations equal each other, put everything on the one side because we recognize it's a quadratic, which is typically what you are going to find in these styles of problems. And then instead of actually solving for x value, we used the discriminant to talk about how many solutions a problem might have, which is slightly different. But that lets you focus a little bit on exactly what you're looking for, which is the number of solutions, not necessarily what they are. At no point in this question did I actually work out how many solutions there were to the problems. At no point in this question did I actually work out what the solutions are. I definitely worked out how many, but I don't know what the solutions are. I would actually have to go back with the k value subbed in and actually solve for x in order to find them. But that's way outside the scope of the questions that you're usually asked. So I hope this made a little bit of sense. It's always good to have a worked example in front of you. Maybe go back and watch this again, take your time with it, try and figure out exactly what's going on in terms of all the algebra, make sure that all of that is squared away, make sure that you've got a handle on how to deal with quadratic problems because they are going to keep reappearing in all sorts of capacities as your year goes on. So anyway, guys, I hope this really helped. Let me know if you've got any comments, questions, thoughts. Just whack them in whatever comments are available, wherever you happen to be watching this, whether it's Facebook or YouTube or whatever. Just let me know, or otherwise flick me an email, ask me more questions. I love answering problems like this, so the more that I get, the happier I am. Anyway, guys, thanks very much, and I'll catch up with you next time. Bye.